I'm Ali. I'm a data scientist at Bueller, and I will speak about digital twins as enabler for data-driven process improvements in the industrial manufacturing of food and feed. Before I dive into data and digital, I would like to start talking about climate change. For some of you who don't know what's the Earth Overshoot Day, this is defined as a day every year where humanity's demand for ecological resources in that year exceeds what the Earth can regenerate in that given year. In 1970, that was on the 31st of December. Last year, that was on the 29th of July. The Intergovernmental Panel on Climate Change, or the IPCC, has released last year the first of 3 installments of the 6th assessment report. And this is some of the things that you can see as facts we are facing today. The CO2 concentration is at the highest levels in at least 2 million years. Sea levels are rising at the fastest rates in at least 3,000 years. Arctic sea ice areas are at lowest levels in at least 1,000 years, and glaciers are retreating as unprecedented in at least 2,000 years. So how many wake-up calls do we need to start acting and save our planet? I don't want to go into too much details here, but this is one of the main outcomes of the UN emissions gap report, was released on 2021, which is that if we want to limit global warming to 1.5 degrees in this century, then which is actually the main goal of the Paris Agreement, then we need to reduce global greenhouse gas emissions by 50% just in the next 8 years, so by 2030, which is of course a huge challenge for all of us. Emissions come from many different sectors, as you know, like one of them is transportation, of course, then there's things like buildings, industry. One of the main ones is actually food production, and this is responsible for around a quarter of all of the global greenhouse gas emissions. This is coming from different sectors also, let's say in food production. So one is land use, crop production is another one, livestock and fisheries around 30%, and then supply chain, including food processing, is around 18%. There's, of course, many mitigation options to reduce this. One is, for example, lifestyle changes, moving towards more plant-based proteins and meats. Another is doing things more efficiently, like, for example, more efficient raw material processing, or more efficient agriculture, more efficient supply chain. So who we are at Bueller? We are making technologies, production plants, machines in 2 different industries. One is food processing, and the other is advanced materials. We have a huge global relevance. We are responsible for feeding 2 billion people and moving 1 billion people every single day. And currently in the world, we have around 8 billion people, but it's estimated that in 2050, we're gonna be 10 billion people. And the big question is, how can we feed all of those people sustainably while also meeting the IPCC targets? So our commitment is to make technologies that reduce energy, waste, and water by 50%, and also to provide the industry with technologies that emit 50% less greenhouse gases. Of course, this we can achieve in many different ways. One of the things, if I think about, again, the mitigation options, like the lifestyle changes, we are working on a lot of technologies in the plant-based protein sector, for example. Another one, which is the main topic for today, is digital. But how can digital help? So according to the Global E-Sustainability Initiative, ICTs, or Internet and Communication Technologies, has the potential to reduce all greenhouse gas emissions by 20% just in the next 8 years. ICTs can achieve this by helping companies and consumers better use energy and more efficiently use energy. Of course, digital centers which are used to power services, data centers that are used to power services, they contribute to the emissions, around 2% actually, but this is estimated that it's actually 10 times less than what we can reduce by using those digital services. Usually when we talk about digital, we are talking a lot about AI, data science, machine learning, but AI and data science don't come from scratch. There is a lot of digital groundwork that's required to reach full data science maturity. You can think about this as a pyramid. So on the down layer, you have data acquisition. You start by collecting the data. Of course, you can use like standard connectivity solutions. You get the data, make sure the quality is good and all of this. Then you go into data engineering. You want to store the data, also data lakes, databases, all of this. You want to make sure that you can access it. Also, for example, using standard APIs. Then you go to master data management and governance. As an example, there is FAIR principles. Then you can start making things from this data. First, you can do things like reports, dashboards, business intelligence, and this, of course, gives you a lot of transparency and also makes your services digitally enhanced. And finally, you can go even to more advanced AI, machine learning, more advanced data science, where you can do things like self-optimized operations and more business transformation. Actually, today I'm going to speak about 2 use cases at Buehler. One is a little bit more on the 4th tier, which is the reporting and business intelligence, and the second is more on the machine learning and AI. This is also an example of how a high-level architecture of an Industry 4.0 cloud platform would look like. This is actually from Buehler Insights, which is our official customer-facing digital services platform. So on the left side, you can see there is actually the connected devices from our installed plant base in the globe. We collect data, send it through gateways to some storage accounts, data lakes, and there this data is being processed. We come up with many different use cases of added value to the industry, to our customers, and then those services and use cases we are sharing with our customers on the Buehler Insights portal. Before I jump into the use cases, I just want to show you a 2 minutes video. It's on how actually digitalization can be done in the traditional industry, and this is an example of a grain mill, one of the Buehler's grain mills in the UK.
Flour consumption in the United Kingdom comes in at around 60 kilograms per person per year. While the range of products is seemingly endless, consumers have one thing in common. We all want peace of mind, knowing that what we and our loved ones eat is safe and of consistent highest quality. With an annual output of around 1.4 million tons of flour, Whitworth Brothers Limited is well aware of its huge responsibility as the UK's biggest flour producer. Thanks to possibly the smartest mill in the world, they can live up to the highest standards they set themselves.
What we have in operation here today marks the beginning of a new era in flour milling. We can digitally monitor all our processes throughout the smart mill. The E3 concept is really a step change away from the traditional way of operating a flour mill. It allows us to challenge the boundaries and to continue moving forward with the smart mill technology and just to really expand the opportunities within milling. Back in 2018, we met with Buehler. We've had a long-established relationship with Buehler and we've enjoyed that collaboration. And Buehler presented to us a vision of E3 and smart mill, and we had no hesitation but to join Buehler on this journey, and we're very excited to be here today to talk more about E3 and smart mill.
Mill E3 actually delivers against the 3 new efficiency levels. I mean, space requirements, time, and in particular also energy consumption. And we try to achieve that with a modularization, to modularize the Arias, for instance, the airlock model, the blower model, and other models. And of course, on top of that, we make the plant smart. For instance, here at Whitworth, we have more than 15,000 data points that we use and constantly work with those data. The possibilities are almost unlimited. We brought it now together with our great partner Whitworth from vision to reality. We created already measurable benefits for our customer, and now the journey has just started. In particular, around smart mill, around digitalization, we create constantly new ideas, new products, how we can support the miller, and of course how we can help him to make better decisions.
I know this is a little bit of a marketing video, and I'm not here really to sell you grain mills, but if you're interested, just let me know. So let's dive into the 2 use cases I want to show. The first one is on digital twins. And there's a lot of different definitions of digital twins out there, but this is our definition. So it's a sufficiently accurate representation of a physical process in the virtual space that can be used to model and optimize the performance of the physical process. This is Bueller Insights Replay, and you can think about it as the replay service of your TV provider. So you can just really go back to any date and time and replay the visualization of a plant control system here. So what you can see on the screen, this is what the operators see in their, like on the PC in their control room. It's just like the control system of the plant. And this is from an animal feed plant. This is a mixing line actually of an animal feed plant. It's like really, really easy what's happening there. So here we have like the silos storing some raw materials, and then those are scales, 2 scales that dose those ingredients. So for example, you have a vitamin that you need 5 tons of in the mix. So the scale measures those 5 tons. It's the target weight, and some mixer here where it gets mixed, and then it goes in another line where it's pelleted, and then it's actually animal feed at the end. This is basically replay. Now we are not playing anything. You can see it here, like the down here. It's not pressed. The play. This is why you can see things changing. It will be pressed in a bit, but you can like press on any variable here in the line, open the trend also of it. Here, for example, the color code is for the status. So the scale was red, means it was faulty. This one is active, for example. Now we went -5 minutes to check what was happening before it was a faulty scale. And then now if you play it, you can even see things start changing. Like you see it's playing now, like the scales are dosing different materials. And yeah, that's basically it. So it gives you like full transparency of what's happening in the production plant. But more important than this is the amount of data that we gather from it. So from the average size plant, we get around 7,000 different variables. And we have many, many plants connected from our different businesses like feed milling, grain milling, and others. And we can do like a lot of work, like many different use cases with this data. This is one that I want to just talk about today, and it's called Companions. So we built a pipeline for generating automatically reports for different businesses. In that case, it's a feed business. And those reports would contain data-driven plant optimizations. For example, you can have things like plant performance analysis, dosing scale efficiency, which is something I'm going to speak about in the next slide, pelleting line summary, error and downtime trends to check the different faults that were happening, what is the reason, to try to reduce the faults in the future, and then increase the uptime of the machines, for example. So for the dosing, health monitoring, here you can just see histograms for the deviation from the target weight. As I was mentioning, this is like a batch process, and then you have, for the ingredients, you want to measure a target weight that will be in the mix. So if you have like one ingredient, you want to measure 20 kilograms of it, and the scale measures 21, dose is 21, then this is overdosing. Otherwise, like if it's dosing 18 kilograms, then it underdoses by 2 kilograms. And you see here, for example, this one, this is an ingredient that was dosed on this scale. This is the number of batches that were done. Like you see many different batches. Actually, like each one of them is actually a batch, and you see it actually overdosed a lot, which is really bad because that means you wasted a lot of money. Many of the raw materials are really expensive, like vitamins, for example, and you might affect the quality also of the product, which is bad. It's just like a lot of waste raw materials. And just using this plus understanding the root cause of the overdosing, we actually saved 60% overdosing, which is huge for our customers. Another example I just want to show is also how we could detect anomalous dosings. And here we do anomaly detection on the dosing curves themselves. A dosing curve could be like based on the speed or like on the target weight. And here you can see like the difference between like the good dosing curves, which is this one of those blue ones, for example, or the red one. And we used the dynamic time warping technique in order to capture anomalies in dosing. The second use case is on how we could use machine learning for better or more resource efficient raw material processing. And this is an example from our coffee optical sorting business. So what's an optical sorter? You can just think about a sorter as a binary classifier. So it's classifying grain into good or bad. You see the grains flowing in kind of a 2D space, and then you have the red ones or the bad ones. There's cameras capturing color and shape characteristics, and then classify in real time if it's good or bad, then calculates exactly where is the distance, and there's an air pulse that ejects the bad ones. So this is happening in real time, like really quick, and there's a lot of different channels in some of the sorters, like the big ones, and they can even process hundreds of thousands of rice kernels every second. So they run at a really high capacity. As I mentioned, the sorters take or measure shape and color features from the cameras, and how this was set up, like how the classifier was set up, was a little bit based on manual rules from the operator who knows, or the process experts who knows very well like how a good or a bad grain looks like. So for example, they would think that if the circularity is like this and the color is like that, then this should be good, otherwise it's bad, which is of course not the best approach. Especially that there's not one single feature or even few features that provide the perfect separation. So usually you should use a couple of features to provide the best separation, and this is where we use the machine learning approach to do this, to find the best combination of features that provide the best possible separation, and then set up the machine based on this. And using this, we have achieved 20% better accuracy, 3 times less waste, so throwing away the good product 3 times less. And you can see here like how an input would look like with like some woods in there, and then how should be the accept and the reject. Just also to mention some of the other things that we are doing. For example, precision storage. We are monitoring silos to make sure that raw materials and products are stored in an efficient way, and by this we significantly also reduce damaged product. For example, we are working on state-of-the-art technologies that reduce significantly the electrical energy consumption in some of our very energy-intensive processes. Precision sorting, cleaning, and dosing. This I spoke about one example, but this is just one example of many. We have other examples for sorting where we are using deep learning, for example, and finally yield increase, which we are also working on in some of our processes. So just as a summary, analytics and AI is a key enabler to enhance efficiency of food and feed production lines. We have a huge installed plant base, thousands and thousands of production lines. So any small improvement that we can do have a huge global impact. Even if we increase the yield by 1%, we have thousands of machines, so this scales really huge. And we are further developing, as I mentioned, next-gen data-driven technologies to boost raw material efficiency and also to decrease energy consumption in some of our energy-intensive processes. We are not doing this alone. We have an amazing ecosystem also around us. We are partnering with the SDSC, Arcanite, for example, Microsoft for the cloud services, and we have an office here in the EPFL Innovation Park where we are doing a lot of data science. Thanks, everyone. Questions?
Thank you, very impressive. But I think for me, regarding the data acquisition, I'd like to ask you how do you have this big ecosystem? Is it like by company, or can you merge all this data from specific machines? I just wanted to understand how you collect the data in terms of data acquisition.
Mm-hmm. Yeah, I mean the data comes from different sources. Big part of our data, mainly our data is like IoT sensor data. So we have, for example, automation systems in all of our plants, and then Bueller Insights gateways kind of are sending this data from like the plants to some like data lakes there, where we have like all of this architecture and infrastructure to basically process this data, put it in databases so that it's easier for data scientists to work with. But big part of the data is coming from like our customers' plants, from all of the sensors in the plant, from the automation system, and yeah, everything there.
Okay, thank you.
Any other questions, comments?
Yes. Yeah.
Are you exclusively working for food industry?
You mean like in the data science projects at Bühler, or no? We're doing both food and advanced materials also, because we at Bühler, we are actually in both industries, mainly in the food industry, but also in advanced materials. So we do things like, for example, die casting. So those huge machines that do aluminum casting of car engine blocks, for example. Like this is one of our businesses in advanced materials. And there also we do a lot of data science. But here I'm just focusing on the food and feed part.
And are you working for small and medium enterprise or only big one?
No, I mean, we are a big enterprise, maybe not very known, but because it's a little bit business to business more. But we work usually very closely with our customers. And those, I mean, our customers have Bühler machines at the end of the day. Like, for example, I don't know, Lindt. If you think about Lindt, they are one of our customers. So they have the machines to make chocolate from Bühler. And we work together with them by collecting the data from those machines and making use cases that would have a huge value for them.
Thank you.
Sure.
Maybe just a general question. So here you give the example of a very automatized process with, well, mainly machines. But do you have other examples when there is more human intervention? And in this case, how would you factor in the human aspect in your analysis?
I mean, many of the things that we develop are still kind of a human in the loop. So it's currently, especially in those kind of industries, it's really hard to make something fully automated. It's really hard. And sometimes you face a little bit of challenge to convince the customers, for example, why would they run something fully automatically? And this is why many of the things that we do are still kind of a human in the loop. So we give recommendations, or even like in this report pipeline that I was showing, there's many things that we know that, okay, we could run, for example, your schedule, you can run it like this job should be before that job, but this is not automated, you know, like in the plant control system that it's running them like this, because like the operator they are not like yet fully convinced or confident about this, and this is why many of the things are actually human in the loop in such cases. Of course, I mean, in the cases like when we're talking about single machines, like the sorter that I showed, this is completely different because it's a way to more like really classify in real time. But when you look at the whole plant, running it kind of automatically, this is still the next step further.
So maybe another question, can you infer the influence of, well, the human influence just based on the parameters you can measure on the machine? I mean, how do you do? What would be the best advice you'd give if you have to have an idea of the human contribution to what you're measuring?
I mean, we can do it, of course, based on some of the key parameters that we measure based on, and that we can, let's say, grade the machine performance based on. So, for example, yield of the machine. We can have like some algorithms that would recommend to run some process in a specific way to increase the yield of the machine. And then when we recommend this to the operator, or there's like someone who is telling them that this is how you should run it instead of that, then we measure this based on some of those parameters. Like we see if the yield increases or not, then okay, like if it increases, that probably this is a good approach to do it. Otherwise, we need to kind of change the approach. It's a little bit like this.
Thank you.